Good morning. This is Engineering Statistics and Linear Algebra, 18EC44, Module 4, Lecture 10, Linear Transformation, Rotations, Projections, and Reflections. In the last two lectures, first we have tried to consider the linear transformation, wherein we have considered some basic functions such as the differentiation, integration, and then multiplying by a polynomial. And in the second lecture, the same things how we can represent the transformations by means of matrices is what we have considered. And then now we will try to go in more detail where we can see the what we call transformations, which correspond to rotation, projection, and reflection, and how these can be represented in terms of matrices. And if we try to square each of those what we call rotation and projections and reflection, what we are going to get. So here we will consider that the cos theta is equal to C and sin theta is equal to S as the short form for cos theta and sin theta. So first we will consider the rotation through an angle theta. In the figure, we have considered here the two basis functions 1, 0 and 0, 1. 1, 0 is this and 0, 1 is this. So by rotation of this 1, 0 vector, which is having one value in the x-axis and 0 value in the y-axis, then this will be rotated by theta to get this value over here. So length of this vector remains same as we have here, right? So if this the what you call value corresponding to this vector will be, if you project this down, 1 into this is the base and this is the hypotenuse. So 1 into it will be cos theta, and that is C. And if you project this onto the what you call y-axis, then theta will be here, this theta will be here, and this will become the opposite, and the you have the length of this as 1 into the opposite quantity, which is sine, will give us the value of S in the y. So therefore the x component will be C and the y component will be S over here for the basis which is 1, 0. Similarly, the basis 0, 1, which is this vector having length 1, will be transformed into minus SC after rotation by an angle theta, minus SC by a rotation of theta. So if you rotate this by theta, then you will get this, and the length of this will again be 1. And if you project this onto this over here, right, this is theta, so therefore this will be theta, right? So opposite to this is what we have, this, and this is your x component, and this x component will become opposite. Opposite is sine, so sine, but in the negative direction, therefore it is minus S. Whereas this projected onto the y-axis is going to give us, this is theta and this is the base for this hypotenuse, and hence the base will give you the cos, and 1 into the cos will give us the value cos itself, which is C, onto the y-axis. So on the x-axis you'll have minus S, and on the y-axis you'll have C. So thus the basis 1, 0 is transformed to CS, and the basis 0, 1 is transformed into minus SC. And on the whole, if you put both these CS and minus SC, you're going to get the rotation matrix as CS and minus C, minus S and C in the two columns of the rotation matrix. Now, if we will try to put a few of the questions, does inverse of q theta equal q of minus theta is what we will see. That is, q of minus theta is rotation backward. If you take the rotation in the forward direction and then you take the rotation in the backward direction, do we go back into the same place, is what we need. Yes, whether that is true at all. The answer for this is yes, because of the reason that if you multiply q theta with q minus theta, then you are going to get a value which is the identity matrix. So q theta is nothing but this itself, and q of minus theta is wherever, what you call, cos of minus theta will be cos, sine of minus theta will be minus sine, and that's what is mentioned over here. Cos of what you call minus theta is cos itself, sine of minus theta is minus sine, and you have another minus over here, hence it cancels, minus s will become s. S will become minus s because sine of minus theta is minus sine theta. Cos will remain cos because cos of minus theta will be uh, cos of theta itself. And if you multiply this with this, then you're going to get a 1, because c into c will be c square, minus s into minus s will be plus s square. So c square plus s square is cos square theta plus sine square theta, that is equal to 1. And if you multiply this with this over here, you'll get cs plus of minus sc, and that will be cancelling, and hence we'll get a value 0. Similarly, this multiplied by this will be sc plus of minus cs, and that will become 0. Then this multiplied by this will be s into s square plus c into c square. So sine square plus cos square will be again equal to 1. That's why you have 1 over here. In the same way, does the square of uh, uh, q theta equal q2 theta is what we will try to see. That means if you rotate first by theta and then rotate once more by theta, will it correspond to rotation of 2t? It should be naturally s, and that can be proved over here by the set of equations being mentioned over here. So q theta is this itself, and another q theta is being mentioned over here. And if you multiply this, you're going to get this, that is c into c is c square, minus s into s will be minus s square, c square minus s square is nothing but the cos 2 theta, and then you have this multiplied by this, that will be c into minus s plus of minus s into c, that will give you minus 2cs, and 2cs or 2sc, 2 sine theta cos theta will be equal to sine 2 theta, and with a minus sign you can try to write that. Similarly, this multiplied by this is going to give you this quantity, and this multiplied by this will going to give you this quantity, and this you can see turns out to be the same thing, except that the angle is 2 theta. The transform q itself, because cos minus sine 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 and cos only that in place of theta you have 2 theta. Then another question is, does the product of q theta and q phi, two different angles, lead to the combination of the two angles together equals q of theta plus phi, that is rotation by theta and then rotation by phi. Does it lead to rotation by theta plus phi at all, is what we need to consider. Yes, it should be true naturally, and that can again be proved by considering the q theta multiplied by q phi. So in each case now we can write cos of theta. In the first one, q theta, you can write cos theta. This is minus sine theta, cos theta, and for q phi you can write cos phi, minus sine phi, cos phi, and then try to multiply them. You are going to get this over here, and which definitely turns out to be the what you call rotation by theta plus phi. So from this we can what you call digress the statement written over here. Suppose we have A transform which transforms from V to W, and B which transforms from U to V. Their product AB starts with a vector small u in U, goes to BU in V, and then finishes with AB in U in W. This composition AB is again a linear transformation from U to W, from U to W. Its matrix is the product of the individual matrix represented by A and B. Similarly, we can discuss the same thing about BA also. Now let us take the next one, which is projection. Projection onto a theta line. So this is a theta line onto which the basis 1, 0 is to be projected and the basis 0, 1 is to be projected. This basis and this basis is to be projected. So from figure 1, 0, that is this vector is projected onto C square CS. From here it is projected to this point. So remember that the length of this is here, uh, in the x direction is x and is 1, and the length of this in the y direction is 0 for this. That's why we call this as 1, 0 vector. So whereas when we project this over here, naturally this is the base corresponding to this hypotenuse, and the length of this will become the cos C, cos or C. The length of this is C, and this again projected to the x-axis over here will give us cos into again another cos, okay, cos into the another cos over here, whereas this projected onto the y-axis will give you this is theta, and therefore this angle should be theta, and therefore this should be the opposite, and uh, this itself is cos, and this projected onto the y-axis will be sine. So it will be cos into sine, and that will be CS. So this will be this point projected over here will give you C into C square, and this will give you C into S, that will be CS, and that can be represented by this term over here. Similarly, the basis which is 0, 1 at this point, when this is projected onto the theta line, then we are going to get CS into S square like this. Now, if you see over here, the length of this in the y direction is 1, the length of this in the x direction is 0, and if this is projected onto this, then theta, the theta over here goes to this place, and this line is over here opposite to the theta, and that corresponds to, because it is opposite, it corresponds to sine, and once that is sine, then this point is again the x component of that is the one which is projected over here. So sine into cos, and the y component of this is projected over here, that will be sine into sine. So sine into cos is CS, sine into sine is sine square, and that's what is being mentioned over here. Sine into cos or cos into sine is CS, and then sine into sine will be S square. So thus 1, 0 vector basis is projected onto the C square CS, and the second basis 0, 1 is projected into the CS S square. So thus we will get the P or matrix which is something like this: C square CS and CS S square, C square CS, which is this, and CS S square, which is something like this. So if we take the square of this P, which is written over here, then we'll get the what you call matrix something like this, and where C square plus S square is equal to 1, and hence we get back the original 1. So that means if we what you call project a line twice, then we are going to get the what you call same projection. That means we can't project once more. So that means if you have a line over here, and if we project this point onto this, any point onto this, further projection onto the same thing does not have any meaning. So that means we will get the same thing, single projection itself. So projection twice, thrice, or 4 times will give us the projection single time. That's what it means over here. The third one which we consider here is the reflection of reflection corresponding to the matrix, which is H, reflection represented by the H over here. So reflection through the theta line is what we are trying to consider over here. So this is the theta line, and if this is the basis and this is reflected here over here, and if we have the what you call basis as 0, 1, and this is reflected over here. So we can what you call solve this from the first principles, but it's easier to consider that h is equal to 2p minus I, and that can always be proved. And if you take that, then you will get the what you call the 2p what you call minus I as the two different things over here, 2p minus I as the value 2c square minus 1 and 2cs which is calculated from here, and the 2cs and 2s square minus 1 which is calculated over here. So we will get the value of h to be 2p minus 1. So image plus the original will give you twice of the projection. This is a standard format. Image, this is image, and this is the this is the image, and this is the original, and that is if both these are added, then you'll get twice of the projection, and that's what is being mentioned over here. So if you try to square this reflection, then we will get 2p minus I whole square is equal to 4p square minus 4p plus p, and p square is nothing but p itself. So 4p minus 4p will cancel each other, and we'll get a 0 here, and 0 added to the I will give you the identity matrix itself. So h square will give you the what you call I. So what it means is, if you have a particular point, and if you take the reflection of this once, we'll go to this, and if you take the reflection back, we'll come back to the same place. Similarly, if you have a point over here, and if you take the reflection of this, you'll get over here, and if you take the reflection once more, you will be back to the same point, and that's what is being mentioned over here. That means if you take the h square, then you will get back to the original position. You will get back to the original position. With this, we come to the end of the lecture.